Welcome back to Mathematics Lifeline. In today's video, I'd like to cover U-substitutions and when we'll use them. So U-substitutions are basically the chain rule for derivatives. It's a very similar concept. They're basically used when the input of your function is not just an x. It's not just a single variable. So it can be its own function in the input. So we use this to make the integral into terms of one variable, then we can integrate it much easier. So there's a process to it. I think reading it with the words is a lot more confusing than actually doing it. So we'll do a couple of examples. But essentially, you're going to start out choosing a function to be your u. So once you do that, you're going to differentiate the u with respect to x. That'll give you a du equals something dx. And then you're going to solve for dx so that you can plug back in. And that's how you can rewrite the integral in terms of u. So then when you rewrite it, you're able to integrate it with respect to u. And then you get your integral, and then the last step, just plug the original function that you chose to be u back in, and then that'll be your final answer for the integral. So the process isn't that hard. It just looks hard when you read it like this. So we're going to go ahead and do a couple of examples. So let's do this example right here. Okay, so the first example we want to do in this video is the integral of cosine of 8x. So when you look at this, you remember the cosine of x is just going to be sine of x. The problem with this is we have an 8x. And so the integral of this is not just sine of 8x because there's this factor of 8 that we have to deal with, just like in the chain rule. So we're going to choose essentially the problem to be our u because we want to change that into something we know how to use. So if we set 8x equal to u, so u equals 8x, then we've done our first step, we've chosen it. So now we want to go ahead and differentiate this with respect to x. So du is equal to 8, which is the derivative of 8x, and then just dx. So now we want to solve for dx. That way we can just plug right in. So if we take du and divide it by 8, we're going to get dx. So now with this, we have this 8x right here that is in terms of a u, and we have the dx, which is in terms of du. So now we can rewrite the integral. So now we're going to have the integral. Cosine is going to stay the same. We didn't change that. But remember, now 8x is our u. So this becomes u. And then our dx is going to become du over 8. So we have du over 8. Now this part looks a little confusing because the du isn't simply just a du. But we can remember that this is just a factor of 1/8 because du is being multiplied here. So this is the same as the integral of 1/8 cosine of u du. And with that 1/8, it's a constant, so we can pull it out to the front. So we have 1/8, the integral cosine of u, du. And this is something we know how to work with. The u is just one variable, so we're able to integrate that just in the normal way. So the 1/8 stays there, it's just a constant. So we have 1/8 sine of u plus c. So that's the fourth step. And so now the final step, we're just going to plug in our 8x back in for u. So our final answer here is just going to be 1/8 sine of 8x plus c. And that'll be your final answer for the integral. So you can see that it's not just sine of 8x. We still have that factor of 1/8 because we have a factor of 8 in the input. So the u-sub is a way that we can deal with that in a much simpler way. So let's go ahead and do another example. Okay, so the second example we want to do is x over the square root of x squared plus 1. So when we look at this, obviously we see that square root in the bottom and it looks really complex. So we're essentially looking for a way to simplify that to where we have something in the form of something we know how to use. Because this is just a super complex denominator here. So we see that that's probably going to be our problem. So we're going to set u equal to the input here. So u is equal to x squared plus 1. So now we have to differentiate it. So du is equal to 2x dx. So now what we can do is divide everything by 2. So we have du over 2 is equal to x dx. And the reason that I did that is because we have an x dx in this integral. X times dx is here, x times dx is here. So this is going to be way easier to rewrite. So essentially we can rewrite this integral in terms of u now. That's the third step. So we know that this x dx turns into du over 2. So we can set that over here. And then we still have the fraction. We're going to put 1 on top. And then we have the square root of u, because this turns into u. So we have 1 over the square root of u times du over 2, which, remember, this is equal to 1/2, the integral, of 1/2 times 1 over square root of u du. And we can pull that 1/2 out. So we have 1/2 times the integral of 1 over square root u du. So now with this, we can use exponent properties in order to make this into something we can use the power rule on. So this is the same as 1/2 times the integral of u to the negative 1/2 power du. And remember, because this is to the 1/2, and since it's in the denominator, it's negative 1/2. So now we can use the power rule. So we end up with 1/2 times the integral of this right here. So this is going to be, we're going to add 1 here, so which gives us u to the 1/2 over 1/2, which is going to be equal to 1/2 times 2 u to the 1/2, and then plus c, because we integrated. So now these 1/2 and this 2 will cancel. We end up with u to the 1/2 plus c, which is equal to the square root of u plus c. And now all we need to do is plug our u back in. So our u is x squared plus 1. So our final answer is the square root of x squared plus 1 plus c. And that will be your integral for that. So again, it's still a pretty tough problem, but we're able to deal with this x squared plus 1 in terms of just a u. And that's really helpful in the scheme of things. So let's go ahead and do one more example before the end of this video. Okay, so the last example I want to do for this video is the integral of tangent x. So with this one, it's not clear that we need to use a u sub right now, because we see that the input is just an x, which is it's something that we like. But we need to realize that the integral of tangent is not an elementary integral. It's not like the integral of cosine where we know it's just sine. It's something more difficult. So the problem here is the tangent. So we want to fix that problem. So the way we're going to do that is, remember that tangent is equal to sine over cosine. So we're going to rewrite the integral. So this is equal to the integral sine x over cosine x. So now we're going to do a u sub, and I'll show you, it's not very clear for this one, but I'll show you why we're going to do a u sub, because it works out perfectly. So if we set u equal to cosine x, so u equals cosine x, then we need to take the derivative of that. So du is equal to negative sine x dx. And the only thing we want to mess with on the right side is the negative. So we're going to make this negative du equals sine x dx. And the reason I chose u to be cosine x was so that when we took the derivative and we moved the negative over, we have something that's in the integral. So we have a sine x dx here, and we have a sine x dx here. So because of that, we can rewrite everything in terms of u. So let's do that. So here's the third step. We're going to rewrite everything in terms of u. So we know our cosine turns into u, so that's on the denominator. And then we have this sine x dx that turns into negative du, so that can go on the top, negative du. And so now, the du can just be moved over to the side. So this is the same as the integral of negative 1 over u du. And we know what the integral of 1 over u is. It's going to be ln of u. So negative 1 over u is negative ln of u. So we're going to end up with negative natural log of the absolute value of u plus c. And then the final step is to just plug in what our u was. So we have negative ln of the absolute value of cosine of x plus c, which is a perfectly valid answer, but we can make this look a little bit neater by using a property of natural logs. So since we have a negative, this can be distributed to the power. So we have cosine of x to the negative first power, which is 1 over cosine of x. So we have ln of the absolute value of 1 over cosine of x plus c, and 1 over cosine x is secant x. So we have ln of the absolute value secant x plus c. And that right there is your integral. Like I said, this is still a perfectly valid answer. I think that's more of a preference for me because there's no negative out front. But you can see that using u sub here is very easy whenever we figure out what we need to use as our u and our du. So sometimes with u sub, you will need to do trial and error. So you won't know exactly what to pick. But one thing will work if u sub is the right method. So Again, in this case, it was cosine x. In other examples, it could be something different. But it's just a way to make everything easier and into something we know how to do. I mean, we know what the integral of this is, but we didn't think we would get there from tangent x. So U-sub just makes everything a lot easier. So that's all I have for you in this one. Let me know if you have any questions, but if not, then I will see you next time.